I appreciate we're like a minute off coffee, so I'm going to whiz through the starting slides as quick as we can. I'm happy to chat through a bit later. But essentially, I'm from the Biomedical Imaging Unit in Southampton. We're a split facility, so we're both NHS and university. We've got 12 members of staff and 2 year and industry students, and kind of work with a range of different bits and bobs. We've got a couple of transmission electron microscopes and a couple of scanning electron microscopes. The one underlined is the one I'm going to talk about today, which is kind of our newest toy in the SEM world. But we've also partnered with our colleagues in MUVIS, and we have a couple of different X-ray histology-based systems and the MyLabs in vivo system in the animal house as well. I'm biased because I'm an electron boy, but we do have some light microscopes that I don't know much about. But we can do live cell imaging, we can do high throughput fluorescence scanning, we've got confocals and we have the light sheets. So before I kind of talk about the system that the hospital photographer came and took because it looked fancy, it's a shout out to our collaborators with Haleon, or previously GlaxoSmithKline, who funded all of this kit for looking at research that they're particularly interested in alongside an old knowledge transfer partnership we've had with them. And essentially, in brief, what they're looking at is sensitivity blocking toothpastes and how we can fill those tubules that run through your dentine with a compound to stop the sensitivity. What's left behind after acid treatment, and that's where they're interested in the elemental mapping. What part of their formulation is persisting after acid erosion? If you'd like more information on the project, my colleague from Southampton, Harwell, was going to have a poster, I think, on board 7, so please go and ask him all the questions. So the system itself is a Teskin Clara FEG. It's a beautiful machine, and I'm not just biased because I have to use it. It is actually really nice to play with. But specifically why we chose this one is that it's really good with low energy beams. We all know there's lots of different types of volume EM, so I'm going to kind of skip through to the point that we've gone for the serial block face with the Connectomics Katana, predominantly because we wanted that large area overview of the sample and to be able to take those multi-ROIs to get the data points that the company was interested in. And just as a kind of a highlight, we've seen serial block face before. This is a beautiful project we've done with this system and the Katana, looking at evolutionary biology of the placenta. And we've been able to kind of correlate to our micro-CT, finding a particular villus in toll blue, relating that back to the 3D volume in the CT, and then picking out our pin structure to do our 3D data set from, which has been beautiful. Most exotic sample I've had so far actually is the giraffe placenta from this project. So we take what is standard serial block face, and then we stick on Oxford Instruments Extreme Detector. We've got the Extreme Detector because it has got about 15 times greater sensitivity to the lighter elements at low kV, and this whole low kV thing is a current theme with this microscope that we need to kind of be mindful of. Just as a quick shout out to where we've used elemental mapping. Normally this is a biopsy of the inner eyelid from one of our patients who had foreign metal in his eye, and we're able to do our EDS maps. And for those that are familiar with EDS, you get your little spectrum of your energy peaks for the elements and how high they are, and then we can relate that back to our image. In this instance is actually on one of our TEMs to be able to identify what those materials might be. So whizzing on even faster because I'm desperate for a coffee. Beautiful animation from our friends at Connectomics that they've let me borrow, but essentially you've got your Teskin Clara, you've got your Katana microtome sat on the stage, and previous talk mentioned how quick and easy these are to fit. They are actually a dream to fit. When I'm used to using a 3-view and changing the doors over was quite bad on my back. This is much nicer, but essentially you have your pin with the sample, you've got your diamond knife shaving away, as you all know. The only difference is when we have our image being taken by the Teskin, there's a slight pause before the next cut, and then we go over to Oxford Instruments, who then take our elemental map. So we're building up 2 images simultaneously, one after the other between each cut, so we get those 3D data sets. So as an example of that, this is some solder, metal solder, that Connectomics provided the data for. And my handsome colleague in the top corner, who's another tall, bald man in the BRU, David, has done this lovely little reconstruction for me to show 3 of the elements that we have the data for. It's serial block face and EDS on every slice, and as we go through the data set, we're able to then kind of look, in this case, we can go for bismuth, take out that element, we can render it with thresholding both in the SEM and with the EDS map, and we can get some quantitative data from that. You see they're not perfect, there's a little discrepancy between that, and I'll kind of talk about that in our the faults and pitfalls that we've kind of found with this system. But we can get some really nice resolution on it. We can kind of get good segmentation with basic image J thresholding. And when we come to overlap them, they're fairly good, actually. They're not bad when you compare elemental map to the SEM image. There's a slight offset, but again, we can kind of discuss that at the very end. So then I'm a biologist, so I don't like mixed metal stuff. I want squishy things. So here's a piece of human brain. It's only a short data set, but this was one we collected at Southampton. And we're just using the heavy metals that we've stained for serial block face sectioning anyway. The myelinated axons show up really nicely with the osmium, and the red blood cells with the lead and the osmium combined. And when we chuck in the elemental maps, what you'll notice this time is we haven't done every single slice. We've done every 10th slice as an elemental map. So there's a bit of flexibility in how you want to set that system up. If we threshold to the SEM image, we can correlate to our maps from our heavy metals. And when we see the consistency in slice 1 to slice 10 being the same element, we extrapolate between those two and say, okay, well, that osmium channel's conducted across the axon, and we can kind of map those through that way. So this is the kind of thing I think is most interesting, is our reflections and our learning. Is the big things is sample type. If it's biological, it's going to need heavy metals. So you're going to put a load of elements onto your sample. And if the thing you're interested in mapping is going to be hidden under an osmium peak, you're going to have a little bit of a problem. So we need to think about how we're treating our samples. How hard a sample can be. We can go up to decalcified bone and dentine on a diamond knife. It does wear and tear it quicker than you'd like, but it is manageable. Anything more, we're not brave enough to try. Charging, as we all know and we've heard, is a major issue. This system has to be run under high vacuum because we're using a windowless detector, so it's prone to condensation, so we can't do it under variable pressure. This is the human brain, and in the top image you can see there's a little bit of charging around the top of that vessel, but it's negligible. If we move a few fields of view over to the edge of the tissue, it's horrendous, so we need to be mindful of what we're going to do with that. The other thing to mention is resolution. So optimal settings to get a good SEM image. Down in the bottom, we've got the fine microvillus structure across the edge of the placenta there. If I use the same settings that I'd want to then do an elemental map for with a stronger, bigger beam current for a bigger spot size, etc., you can see it's quite noisy. So there's a bit of a trade-off between the two systems that we have to think about. Throughput is quite an issue, but it depends how deep your pockets are for who's using the facility. The bottom data set is the solder, and that was every slice. The top data set is the brain every 10th. The SEM images for the brain took about 1.5 minutes a scan. The EDS maps take about 45 minutes a map. And once you start doing that in volume, if we're doing like 50 microns, so 500 slices at 100 nanometers, it's a difference between half a day and 15 days, depending on if you just want to do SEM or if you want to do the EDS maps on every slice. So you just have to have a kind of a time consideration as to what that's going to be, and whether or not your data is actually going to change within those 10 slices. So if we say that if we're just following that osmium, we know it's going to stick to those axons, we know they're consistent, so we can get away with doing every 10. Image analysis, this is actually slightly different how it's now set up. This, I should say, is very much a working development. It's under the great efforts at the moment from Connectomics and Teskin and Oxford Instruments trying to polish this system for us. But originally, our SEM data was coming from the Teskin, and the maps were coming through the Oxford Instruments Aztec software. The pixel values to threshold in an SEM image, you've literally got thousands of steps to choose from. You've only got 9 in an EDS map, so the noise difference between a step on the thresholding is quite dramatic. We've now got it so the maps and the EDS are all being taken through Aztec, so the SEM images and the maps have been done through Aztec, and that's improving on this misalignment we saw before where the data sets slightly offset. The pixel sizes are different between the SEM and Aztec. So by trying to get them all together, it makes it a little bit easier to segment. And it also means we can use Aztec's drift correction, which was previously not usable because it needs that SEM image as a reference. So kind of next steps in kind of what development-wise, it is still under development. It's a good system. It's got a lot of legwork to go, but I think we're nearly there now. I'm quite looking forward to the next couple of weeks of play. And essentially what we're really interested in is oral health, because we've got that industry partner looking at the toothpaste. how we could use this to look at diesel inhalation on cell culture models, wound healing with laconite gels in bone repair. There's obviously material sciences applications and our diagnostic workflow for foreign bodies and things. What we're really interested in is how we can reduce this charge, because we have to work under high vacuum. If I want to put a piece of lung in with a lot of empty resin space, I'm going to have charging. So kind of thinking about conductive resins and how we can use local charge compensation would be ideal in this system. But a little shout out to the thanks to the key people behind these companies and my colleagues that have made kind of this happen so far. Thank you.
Thanks, James, for the speedy talk as well to get us to coffee. So questions, maybe a couple of quick ones, and then we can, yeah.
This is very interesting. When you're doing the mapping, so if you're doing a cutting cycle that's a minute and a half cut, a minute and a half cut, a minute and a half cut, that's fairly stable. So the cutting is going to be fairly stable. But if you then got 45 minutes to do the map and then the next cut, do you see any difference in the consistency of the thickness that it's cutting?
We haven't noticed anything massive yet, but as I say, it's fairly early days for the testing side of it. It's kind of only just been fully set up into a workable state that we can leave it alone without it going a bit doolally. So I think give us a month or two to play, and then I'll be able to answer that a bit better. But so far, the microscope stage and the katana seem fairly stable in their general function.
Since you're dealing with a mix of material science samples and biological samples, there are varying hardness. Can you also then, for instance, the katana, set things like sectioning speed, for instance, or adjust the position of the knife, saying, okay, if I don't want to change the knife every year or so, section all the hard things on the left side and section all the softer things on the right side of the knife.
Absolutely, and that works in principle until you get a user that decides that they're always going to make their block faces really big. Because unfortunately, what I deem as small is not what somebody else might deem as small if they're not an electron microscopist, because that's always a pitfall with a mixed user facility.
Okay, well, I think we should thank all the speakers again.